Whenever we're trying to understand or explain something, it's always good to use the simplest model or the simplest definition that we can get away with to explain whatever we're trying to explain. When we run into problems, we have to increase the level of our theory or increase the complexity of our model to explain that. In acid and base chemistry, we run into one of those problems pretty quickly, and the problem comes down to one very, very common molecule. Ammonia is a base. So ammonia, NH3, is a base, but it has no hydroxide to donate. So if we think of an Arrhenius base as an OH donor, how can ammonia be a base? But remember, the formal definition of a base, using the Arrhenius definitions, is a base is a substance which, when added to water, increases the hydroxide concentration of the solution. So let's use water to help us out. If ammonia is added to water, these two molecules can actually react to form ammonium hydroxide. And if we've got ammonium hydroxide, that ionic compound now can dissociate to form ammonium ions and hydroxide ions. And we just found a way to let ammonia without a hydroxide donate hydroxide or increase the hydroxide ion concentration in a solution. Now, this works, and it lets us make ammonia fit into that Bronsted or into that Arrhenius definition of acids and bases, but maybe we should move on to a little bit better definition that doesn't make us jump through quite so many hoops. The Bronsted-Lowry definitions of acids and bases are similar, especially if we think about the acid side. Bronsted and Lowry didn't really have a problem with the Arrhenius definition of acid, so they defined acid very similarly. An acid, in the Bronsted-Lowry sense, is a substance which donates H plus in a chemical reaction. So it's an H plus donor, or H plus is often referred to as a proton when we're talking about acids and bases. So all of the acids that were acids in the Arrhenius definition are also acids in the Bronsted-Lowry definition. But a base in the Bronsted-Lowry definition is now a substance which accepts H plus in a chemical reaction. So it is an H plus acceptor, or a proton acceptor, if you prefer that terminology. All of our hydroxides are still bases in the Bronsted-Lowry definition because that hydroxide can accept H plus to form water. But now ammonia is a base because if ammonia accepts H plus, it becomes an ammonium ion. So Bronsted-Lowry give us a little bit looser definition of base, a little bit broader definition of acid and base, which now, instead of looking at a bulk property of a solution, now we're following H plus. Is the H plus being donated by an acid, or is the H plus being accepted by the base? This brings up an important classification of substances as conjugate pairs. So a conjugate acid, conjugate base pair are two chemical species that are different by exactly one H plus. So if we look at a reaction here, and this is just a shortened version of our ammonia reaction, what is ammonia doing? It is accepting H plus and becoming ammonium. These two species differ by exactly one H plus. And if we think about this as an equilibrium, if we think about this as a reaction going in both directions, going forward, ammonia is acting as a base. In the reverse reaction, ammonium is acting as an acid. So ammonia and ammonium are a conjugate base, conjugate acid pair. They differ by exactly one H plus. Similarly, in this reaction, water, what's water doing? Water is donating an H plus to ammonium to form hydroxide ion. Well, that means that in this reaction, water is acting as an acid in the forward reaction. In the reverse reaction, hydroxide is acting as a base. So water and hydroxide ion are also a conjugate acid conjugate base pair because they differ by exactly one H+. Well, that means water's an acid, right? Well, let's take a look at a couple of reactions here. And these are just very generic acid-base type reactions. And let's identify all the conjugate acid-base, conjugate acid, conjugate base pairs in these reactions. So HA, again, a generic acid, is going to donate its H+, it's acting as an acid, to form A-. Now that is a base in the reverse reaction. So that's a conjugate acid-base pair. Water is, what's it doing? It's accepting H+ to become H3O+, so water's a base. But we just said that water was an acid. Because if we look in our second reaction, what? B, a generic base, this isn't boron, this is just some generic base molecule, is accepting H+ to form Hb+, right? It's conjugate acid. And water is donating H+ to become OH-. So there's a conjugate acid, conjugate base pair. Water is a base. So let's look at those. We've got an acid and an acid and a base and a base and a base and a base and an acid and an acid. These conjugate pairs, right, in each of these reactions. So is water an acid or is water a base? Well, it turns out that water is whatever it needs to be in the reaction it's participating in. Water can act as either an acid or a base. And in fact, water can react with itself, and water does react with itself as both an acid and a base to form H3O+ and OH- in aqueous solution. So when we're talking about acids and bases, and specifically when we're talking about Bronsted-Lowry definitions of acids and bases, acid and base are really conditional definitions. An acid is something which is acting like an acid in the reaction we're looking at. So it's donating H+ in the reaction we're looking at. A base is something that is accepting H+ in the reaction we're looking at. And if we go to a different reaction, the identity of either an acid or a base can change if it's reacting with something that changes whether it's accepting or donating an H+. We're going to be using the Bronsted-Lowry definitions for a lot of the other things that we talk about. In general, they're probably the more useful, generally useful definitions of acids and bases. So let's keep thinking about where those H+ are coming from and going to in the reactions we look at moving forward. I'll see you next time.